Application of Cauchy's residue theorem. Now we can see the evaluation of definite integral using residue theorem. Consider an example. Evaluate the integral over c 4 minus 3z by z square minus z anti-clockwise around the given path. Here different paths are given. First path is mod z equal to, second mod z equal to 1 by 2, third mod z minus 1 equal to 1 by 2, fourth is mod z minus 2 equal to 1 by 2. We can evaluate this integral around each path. Now the function to be integrated has singularities at z equal to 0 and 1. Both are simple poles. The residue at these singularities are given by residue at z equal to 0 is equal to minus 4 and residue at z equal to 1 is equal to 1. Now we can evaluate the integral over each path. Consider the first path. We can see that both singularities are inside the given curve. So by residue theorem, the integral value equal to 2 pi I into sum of the residues. So we will get minus 6 pi I. Come to the second path. Here only z equal to 0 is inside the contour. So again by residue theorem, the integral value is equal to 2 pi I into the residue at z equal to 0. The answer is minus 8 pi I. Now come to the third case. Here z equal to 1 is inside the contour. Z equal to 0 is outside. So again by residue theorem, the integral value equal to 2 pi I into residue at z equal to 1. So the answer is 2 pi I. Come to the fourth case. In this case, neither of the singularities are inside the contour. So by Cauchy's theorem, the integral value equal to 0. Now you can see the application of residue integration. Residue integration can be used to evaluate certain class of complicated real integrals. This is one of the many advantages of complex analysis over real analysis. Now we can consider the first case, that is evaluation of integrals, real integrals of the form. They are the rational functions of cos theta and sin theta. So first we can evaluate integrals of the form integral 0 to 2 pi f of cos theta sin theta d theta, or f of cos theta sin theta, that is a rational function of cos theta and sin theta. To evaluate such integrals, there is a procedure. Consider z equal to z e raised to I theta. Then we can find dz by d theta, that is equal to I e raised to I theta, or d theta equal to dz by iz. With this substitution, the definite integral on the interval 0 to 2 pi becomes a contour integral over the unit circle mod z equal to 1. From this substitution, again cos n theta equal to 1 by 2 times z raised to 2n plus 1 by z raised to n. Similarly, sin n theta equal to 1 by 2i into z raised to 2n minus 1 all divided by z raised to n. This will allow us to convert the given definite integral into a contour integral. So the integral 0 to 2 pi f of cos theta sin theta d theta becomes the contour integral over c over the unit circle mod z equal to 1 f of, in the place of cos theta we can write z square plus 1 by 2z. In the place of sin theta z square minus 1 by 2iz. D theta becomes dz by iz. So the right side becomes a new integral which can be, that becomes a complex integral which can be evaluated using Cauchy's residue theorem. Consider the following example. Evaluate integral 0 to 2 pi d theta divided by 5 plus 4 cos theta. Here give the substitution for cos theta. Cos theta becomes z square plus 1 by 2z. then d theta replaced by dz by iz. So the given integral becomes a contour integral, that is integral over the unit circle mod z equal to 1 dz by d theta becomes dz by iz, then 5 plus 4 times z square plus 1 by 2z. So come to the next step, you can take 1 by I outside, then dz divided by, after simplification becomes 2z square plus 5z plus 2, then that's equal to 1 by I integral over the unit circle dz by, the denominator we can make into the product of factors, that is 2z plus 1 into z plus 2. Then we can calculate the singularities of the function. Singularities are minus 2 and minus 1 by 2. Of these singularities, only z equal to minus 1 by 2 lies inside the unit circle, z equal to minus 2 lies outside the unit circle. So calculate the residue at the point inside the unit circle. So residue at z equal to minus 1 by 2 equal to 1 by 3. Therefore, by Cauchy's residue theorem, integral 0 to 2 pi dz by 5 plus d theta by 5 plus 4 cos theta is equal to 1 by I into 2 pi I into the residue value, that is equal to 1 by 3. So 1 by I into 2 pi I into 1 by 3. The answer is 2 pi by 3. Consider the second example. Evaluate integral 0 to 2 pi cos 2 theta divided by 5 plus 4 cos theta d theta. Give the substitution. Cos theta becomes z square plus 1 by 2z. Cos 2 theta becomes z raised to 4 plus 1 by 2z square d theta dz by iz. Substitute all this in the given integral. Integral 0 to 2 pi cos 2 theta divided by 5 plus 4 cos theta d theta equal to the contour integral over the unit circle mod z equal to 1 z raised to 4 plus 1 by 2I into z square into 2z square plus 5z plus 2 dz. Then you can take this 1 by 2 outside this integral. Let the function be z raised to 4 plus 1 by z square into 2z square plus 5z plus 2. Now we can find the singularities. The singularities are 0, then minus 2, minus 1 by 2. Here this 0 is a double pole, then minus 1 by 2 and minus 2 and minus 1 by 2 are single pole. Of these poles, the z equal to 0 and z equal to minus 1 by 2 lies inside the unit circle. So we have to evaluate the residue at each of these poles. Residue at z equal to minus 1 by 2 equal to 17 by 12. Residue at z equal to 0, that is a double pole. So using the formula, we will get the answer as minus 5 by 4. Then by residue theorem, integral over c f of z dz equal to 2 pi I into sum of the residues. So here integral 0 to 2 pi cos 2 theta by 5 plus 4 cos theta d theta is equal to 1 by 2I into 2 pi I into sum of the residues. So after simplification, we will get the answer as 5 by 6. Next type of real integral is the improper integrals of the form integral minus infinity to infinity f of x by g of x dx with degree of gx minus degree of fx is greater than or equal to. So we can find the method of evaluation. Integral minus infinity to infinity f of x by g of x dx can be converted into a contour integral by writing in the place of x, replace that by z, so that integral, real integral equal to the contour integral over c f of z by g of z dz, where the c is a contour enclosing singularities of f of z by g of z in the upper half plane. So the integral value equal to 2 pi I into sum of the residues of this function f of z by g of z in the upper half plane, where the sum over residues of all the poles of f of z in the upper half plane. Now we can see an example. Evaluate integral minus infinity to infinity x square by x square plus 1 the whole square dx. First, we can write f of x by g of x as x square by x square plus 1 the whole square. Just replace x by z. So f of z by g of z equal to z square by z square plus 1 the whole square. Now find the singularities of this function. So singularities are given by z equal to plus or minus I and plus or minus I. That means z equal to plus or minus I are poles of order 2. Of these poles, we have to choose that pole which lies in the upper half plane. So here only z equal to plus I lies in the upper half plane. So by Cauchy's residual theorem, the integral value is equal to 2 pi I into sum of the residues in the upper half plane. That is equal to, we have to get 2 pi I into, here z equal to I is a pole of order 2. So using the formula, we will get the residue value equal to 1 by 4 I. Then 2 pi I into the residue, that is 2 pi I into 1 by 4 I is equal to 5 by 2. So this is the required answer for the given real integral. Consider this example. Evaluate integral 0 to infinity 1 by x square plus a square the whole square dx. So actually the second case is the integration within the range minus infinity to infinity. Then we can convert the given integral in that form using the result from the integration. That result is if f of minus x equal to f of x, that is f is an even function, then integral minus infinity to infinity f of x dx is equal to 2 times 0 to infinity f of x dx. So suppose if the problem is 0 to infinity, what we have to do is we can evaluate the given problem in the range minus infinity to infinity, and we can multiply the answer by 1 by 2. That is integral 0 to infinity 1 by x square plus a square the whole square dx is equal to 1 by 2 times integral minus infinity to infinity 1 by x square plus a square the whole square dx. It satisfies the above condition. Then, as in the previous problem, we can just write f of z by g of z as 1 by z square plus a square the whole square. And we can calculate the singularities. Singularities are plus or minus ai, plus or minus ai. Then here z equal to plus or minus ai are poles of order 2. Here we have to see the pole which lies in the upper half plane, that is z equal to plus I lies in the upper half plane. Now the integral becomes 1 by 2 times integral minus infinity to infinity 1 by x square plus a square the whole square dx equal to 1 by 2 times 2 pi I into residue at z equal to ai of the given function. So here z equal to ai is a pole of order 2. Then using the formula, we can find this answer as pi by 4 a cube after simplification. Now if the integrals are the form integral minus infinity to infinity f of x by g of x cos mx dx, or integral minus infinity to infinity f of x by gx sin mx dx, then we can see the method of evaluation. Such integrals can be converted into a complex integration using this procedure, that is integral minus infinity to infinity f of x by g of x cos mx dx is equal to the real part of the integral over c f of z by g of z e raised to I mz dz. Similarly, integral minus infinity to infinity f of x by g of x sin mx dx is equal to the imaginary part of integral over c f of z by g of z e raised to I mz dz, where c is a contour enclosing singularities of f of z by g of z in the upper half plane. Consider this example. Show that integral 0 to infinity cos ax by 1 plus x square dx is equal to pi by 2 e raised to minus a. So, here first of all write f of z by g of z e raised to I mz equal to e raised to I a z divided by 1 plus z square. Here it is given. Only thing is just replace x by z, and in the place of cos x you write e raised to I a z. Here in the place of m it is given a. Just write e raised to I a z by 1 plus z square. Next you calculate the singularities. So singularities are plus or minus r. Of these singularities both are simple poles. Then you take the singularity which lies in the upper half plane. Here z equal to I lies in the upper half plane. So integral 0 to infinity cos ax by 1 plus x square dx is equal to 1 by 2 times integral minus infinity to infinity cos ax by 1 plus x square dx. So that's equal to 1 by 2 times the real part of integral over c e raised to I a z by 1 plus z square dz, where c is a contour enclosing the pole z equal to 1 in the upper half plane. Then the value of the integral is 1 by 2 into the real part of 2 pi I into residue of the function at z equal to I. Then we will get 1 by 2 into real part of 2 pi I into the residue value is e raised to minus a by 2i, that is equal to pi by 2 into e raised to minus a.